All right, hello and welcome. Today, we're going to take what seems like a really complicated math problem and boil it down to something, well, something you can just see. It's like a visual puzzle. We're going to learn how to solve these things called systems of linear equations just by looking at a graph. Pretty cool, right? Let's jump in.
So, let me ask you something right off the bat. What on earth do two straight lines on a graph have in common with, say, a roofing problem? I know, it sounds like two totally different worlds, right? But believe it or not, they're connected. And the solution is something you can literally see.
And the answer is, they're both solved by finding one single crucial point. That's really the big idea for this whole explainer. We're on a hunt for that one special spot where two different paths, or two different stories, or in our case, two different equations cross. And that intersection, that is the answer we're looking for.
Okay, so before we can actually find that magic point, we got to make sure we're all speaking the same language. Get the lingo down. So let's talk about what we mean when we say two equations, one solution.
All right, first up is this phrase, system of linear equations. I know, it sounds super technical, right? But honestly, it's just a fancy way of saying we're looking at two or more straight-line equations at the exact same time. That's it. Think of them as a team, a pair of rules that have to work together.
And if the equations are the puzzle, then what's the solution? Well, the solution is that one special ordered pair, that one little xy point that makes every single equation in the system true. It's like the master key that unlocks both locks at the same time. Super important.
Okay, so before we jump into finding these solutions from scratch, let's do something a little easier first. Let's figure out how to check if an answer is the right answer. It's a really good way to get comfortable with the whole idea.
So, imagine this. We've got our system of equations, and someone just hands us a possible answer, a point, let's say the point 25. The question is, how do we know if it's the real deal? How do we check if this key actually works?
Well, it's actually super simple. You just plug the numbers in. We take that 2 and put it everywhere we see an x, and we take the 5 and put it everywhere we see a y. For that first equation, yep, 2 plus 5 equals 7. Check, it works. Now for the second one, a little more math, but yeah, it works out to negative 11. Another check. Because it works for both, we can say with confidence, yes, 2, 5 is our solution.
All right, let's try another one, just to make sure we've got this. What about the point -2, 0, for a different set of equations? Is this the key, or is it a dud?
Now, this is where you have to be careful. Watch this. We plug -2, 0 into that first equation, and hey, it works. 0 equals 0. Perfect. We might think we're done. But wait, look what happens when we try it in the second equation. We get 0 equals 2. Nope, that's not right. And this is so important. The point has to work for every single equation, all of them. If it fails just one, it's not the solution. It's an all or nothing deal. Okay, so we know how to check an answer. We're pros at that now. So it's time for the main event. Let's actually find the solution ourselves, and we're going to do it just by drawing a picture.
And here it is. This is the big aha moment. The solution to a system of linear equations is just the point where their graphs intersect. That's it. That xy point we've been testing, it's literally just the address of the exact spot where the two lines cross over each other.
So how do we do it? It's a simple 3-step plan. Step 1, graph the first line. Step 2, graph the second line on the same grid. Step 3, find the spot where they cross. And just to be safe, check that point to make sure it works. Easy enough, right? Let's see how it looks. So here's our system. We take the first equation, y equals -2x plus 5, and we draw its line. Then we take the second one, y equals 4x minus 1, and draw its line. And boom! Look at that! They cross at exactly one spot. And what are the coordinates of that spot? It's over 1, up 3. So the point is 1, 3. That's our solution right there on the graph.
Okay, this is where it gets really cool. We have this new superpower, right? Let's use it. Remember that roofing problem I mentioned at the very beginning? Let's go back to that and see how graphing can solve a totally real-world puzzle.
All right, so here's the story again. Our contractor goes to the store twice. The first trip, they buy 30 bundles of shingles and 4 rolls of roofing paper, and the total bill is $1,040. On the second trip, they just grab 8 bundles of shingles, and that costs $256. The mystery we have to solve is, how much does one bundle cost, and how much does one roll of paper cost?
This is the magic of algebra. We can turn that story into math. We'll let X be the price of a shingle bundle and Y be the price of a paper roll. So, that first purchase, it becomes 30X plus 4Y equals 1040. The second purchase? That's 8X equals 256. And just like that, we've got our system of equations.
So what do we do now? We do what we just learned. We graph both of those equations. And where do the two lines cross? Right there. The intersection point is 3220. That single point contains the answer to our whole problem. The X value, 32, is the price of the shingles, and the Y value, 20, is the price of the paper.
So let's break that down. The x-coordinate of our intersection point was 32. That means the price for one bundle of shingles is $32.
And a y-coordinate was 20. So the price for a roll of roofing paper is $20. How cool is that? We just solved a real-world pricing problem just by finding where two lines cross on a graph.
So, you've seen just how powerful graphing can be, right? It lets us find that one unique answer that makes two different situations true at the same time. Which gets me thinking, now that you know how to find this intersection point using a picture, what other ways could there be? Are there ways to find that exact same spot without ever having to draw a thing?